Okay, so we'll start with the lecture. The homework is graded, so I'll have it here for you guys to pick it up after the class, and hopefully been able to turn the last week's homework in. Today we're going to look at kind of wrapping up the single transistor analysis, just to give you sort of a summary of kind of things that you've already done during the week and we've done in the lectures. And then we're going to wrap up the small signal models by adding, actually going back to these capacitors that we talked about and looking at sort of the frequency response of the single stage transistor. In fact, kind of looking at the unity gain current frequencies and some of the limits of the transistor as an amplifying element. So just like to go back, kind of, for you, go back in some of the analysis. So we'll do a few examples of the common source plus source degeneration. We did this sort of for the bipolar case. It'll be illustrated to do it also for the MOS case. A sketch for the circuit would be that you have load both in the drain and source, and then you're applying some bias plus the small signal, and then you're taking the output from here. So the way we would draw out the small signal model, some parts of it look pretty similar to common gate or source follower configurations. So we're going to have VI that goes to the gate, and then we have a source terminal. In this case, RS. Now, one thing that I'm missing here is the body connection. In this case, I'll keep it tied to ground, just to make things a little bit harder. And then I have GM-VGS, current source, and in the opposite direction, GMB-VSB. R0, and then I'll have the RD to ground, just because the DC supply is kind of a small signal ground. This is VGS, and this is body, this is VSB. So as we did with these amplifiers, there's essentially three quantities we're interested in being able to use this then as compute the gain of this block and then use it throughout, let's say, a multi-stage system. So we're interested in Rn, which is the input impedance, or in this case, resistance. We're interested in the Gm, which is the overall transconductance. And sort of the definition was I out over Vi for V out equals 0, right? And then we have our R out. And R out, as we said, I can always calculate R out just at this point, and then the overall resistance looking into here will always be that R out in parallel with RD. So I can kind of break things up a little bit so that I don't do too much work. Now, what is Rin for this circuit? Infinity. Yeah, if we apply, even in this case, VI is like my V test, right? So obviously there's no current flowing here. So that VI over that gate current is going to be of 0 is going to give me infinity. Now, for R out, you may notice that we're looking from this side over here, right? So when we're looking from this side, we have to null this independent source, right? So the topology looks very similar to something that we've already done. Which topology is that? So gate will be grounded. Right? So this will be shorted here for R out. And obviously, this side is also shorted. Yeah. So in common gate, our voltage was here, right, driving up. But when I was looking at R out, I had to short that voltage anyway, because that was an independent source. So then the resulting circuit is exactly the same in case where I want to apply V test, then I'm looking at I test, right? I don't care whether I've shorted stuff here or I've shorted things over here. The resulting net circuit is the same, right? So R out will be exactly the same as in the common gate. So R out equals to R out common gate. Now, we'll just do it real quick, just to get you all on the same page. So when we do that grounding, we're going to have grounded gate. And then in the source, we're going to have our RS, and this is going to be still VSB. And now I'll play my favorite trick here on in terms of the Thevenin or Norton to Thevenin equivalent. So I'll turn these two current sources that are controlled. So notice here, VGS is controlled by GM-VGS by this VGS over here. But when I ground this terminal, that VGS is equal to minus VSB. Right? So then I'll just flip the sign of this current to go up and have GM times VSB here. Then both of these add up, and I get one current source that is GM plus GMB VSB. And that into R naught gives me this Thevenin voltage, GM plus GMB R naught VSB. And then I have just this R naught as the Thevenin output resistance. And now, since I'm interested in looking at the R out here, I'll ignore RD for now, and then later I'll just add it in parallel. Right? So I want to stimulate this piece from VT and measure this IT. But now it's nice because so VT, these two are voltage sources. I can easily kind of manipulate that and do a KVL. So VT here is obviously IT dropping on these two resistors. So it will be R0 plus RS times IT. And then just this voltage source, right, which is GM plus GMB R0 times, and then VSB. Okay, I'll write it as VSB, but that VSB is really IT times RS, right? So now this whole side is just a function of IT and some resistances. So my VT, my R out is VT over IT, and it's then just R0 plus RS plus GM plus GMB times R0 RS. And then for all intents and purposes, this part over here is actually the dominant part. So I'm just going to simplify it like that. Okay, so we got ourselves the R out, and now we're going to take a look at the other piece, which is the big GM. Okay, so it's the amplifier GM. Now again, let's write it out. So GM is I out over V in when I ground the output, so that all the current essentially starts coming from that ground connection. So let's real quick sketch a circuit from which we'll be able to estimate that. So VI goes into G, and then we have our source. Again, we have RS and VSB, and then here, okay, I have my R naught, and then I'm grounding this node. So I'm looking at this as being I out. So I'll just write a KCL in this case. So I out, I'll write it as a function of this VSB. I know that I out is also flowing here through RS. So that gives me that VSB is actually I out RS. So my I out will be GM times, instead of VGS, I'll write what it is. It's VI minus RS I naught. And then I'll write minus GMB RS I naught, which is VSB. That's for this current source. And then I have minus VSB over R naught, which is going to be IO RS over R naught. So when I move all the IO terms on the other side, I'll get IO times 1 plus GM RS. All right, let me group these two together. GM plus GMB RS, and then plus RS over R naught, and that equals GMVI. And now our capital GM is just I naught over VI, because we've grounded the output. So this is GM over 1 plus GM plus GMB RS plus RS over R naught. So we can now go and simplify this and say this, well, you know, R naught is so much bigger than RS. So we're going to just take this term out and then have like GM over 1 plus GM plus GMB RS. And then I can claim that, you know, predominantly this factor is then bigger than 1. So this is also like GM over GM plus GMB times RS. So now that we've sort of gotten R out, and then we have GM, now we can compute the voltage gain. And this is sort of the modular fashion. I could have gone and written out all the KVL, KCL immediately to get the relationship between VI and VO. But if you don't go and do this modularly when you get more than one transistor in your circuit, then your KVL, KCL will become a little bit harder. And the whole point of this is to be able to do partitioning. So that if you have a chain of transistors and a multi-stage amplifier, you actually can attack it one by one and apply these tricks to solve gain in each stage, and then you'll be able to kind of solve the whole thing, right? So here, now my AV will be minus GM times R out. And this just stems from the definition that we had that our amplifier had GM and had some R out. So the voltage, so GM V1, right? And then there was here R in and V1. So this voltage must be minus GM R out times V1, right? So my gain is minus GM R out. Now, of course, this is where R out, I haven't added any load. So if I add a load, then that load will show up here as some RL. So my R out will have to be in parallel with RL. That's why I can sort of save this RL for kind of the end. I don't have to include it immediately. I can solve without it and just add it in the end. And then I can go back and plug the expressions that we just derived for. So for GM, we had GM R naught over R naught plus RS plus GMB R naught RS. And then we had, well, let's call this RD because that's what it was labeled. And then we have R out in parallel with RD. And so recognize that this piece over here is actually R out, right? So we can kind of write this out as GMRO over R out times, and this parallel is R out times RD over R out plus RD. So these two will cancel out. And then we have something like minus GMRO RD over RO plus RS plus. And now again, we can play the game of kind of elimination and approximate things out by assuming certain pieces are not that important. And so we can leave minus GMRD on top and divide everything with R naught. So we get 1 plus RS over R naught. So this thing we can eliminate, plus GM plus GMB RS, and then plus RD over R naught, right? Again, this piece we can likely eliminate because RD is much smaller than R naught. So we're left with something approximate minus GMRD, 1 plus GM plus GMB RS. Okay. Keep in mind these, yeah.
So when you have AV equals negative GM times R out,
So the question is the RD here, that's the R load. If we have a two-stage, will that be the R in of the next stage? And the answer is yes.
so in the homework when we had AV of the first.
I think there was a voltage divider that was involved. As you're coming in from RS,
Right.
yeah, you have to do the voltage divider, which is kind of what affects your RN.
Right.
Yeah, but we'll do the cascode example right after this, so that we solidify the knowledge and understanding. But I think, you tried your own ways in the homework to kind of develop and understand it. We're going to do it kind of here just to summarize and seal the deal. So, okay, so what I was about to say here is that depending on the circuit, you'll be doing these approximations. But it's kind of this is just as a rule of thumb that you could kind of take this expression, say in most situations, unless I have some weird resistances, this is kind of what I should be expecting from the circuit. And the idea is that there's some intuition that you can build about these expressions rather than staring at this original one and kind of going, what do I do with all these components? So it's maybe before we kind of go into actually doing the multi-stage like a Casco, just summarize a little bit this inspection analysis and what it's all about. So if we had some kind of transistor network, and pretty soon you'll start seeing these multi-stage amplifiers, right? So there's something here, some V out over here, and some V in. You're going to start analyzing it stage by stage by looking at Rn. Then in this stage, what is the total resistance on this node so that this transconductance can amplify that. So in that case, I'm treating this one as a single amplifier stage. And then again, so I could do it by looking at this R out and this being my R load, and then later apply, or this is called, let's say, R in 2. And then my total gain would, of course, depend on R out 1 in parallel with R in 2. But once I'm done with that, it's kind of like I have an ideal source that drives the next stage. And therefore, then I again have kind of the GM of this stage and then whatever the extra load is in the next stage, et cetera. So that's how you peel off one by one transistor. Yeah.
So in a case for BJTs, would you have a voltage division between the
In which
let's say instead of those two MOSFETs, you have those two are BJTs.
Mhm.
Does that load?
Oh, so the question is, from this node, can I do I have a voltage division? So these resistances will take care of that, right? So the point is that in a BJT, I would be seeing whatever's downstream over here, right? So I would have to kind of estimate what that emitter resistance is, and I know from what I've done previously with common collector stages that that emitter resistance gets multiplied up by a 1 plus beta to be seen from the base, right? So I'm going to be using those kinds of formulas. Yeah. But inevitably, it is true, and even though MOS is an inferior device, some of the calculations are kind of easier with MOS because you can kind of do this explicit isolation between stages. You don't have to worry so much what's down the emitter path, right? Yeah. Okay. So of course, in a simple, so in this analysis, and this is what we've done kind of with some of these basic single-stage derivations, we've always done what we call the simple case. And this is something that pretty much you should be doing always as a first cut, just to understand what the circuit's doing. And then maybe you can add the secondary effects. So in the simple case, we can always assume that GMB is 0, so I don't have the body effect. I can also assume most of the time that my R naught is infinity, maybe except for the very end device where the voltage directly develops on that device. But in this case, by assuming these, you sort of clean up a lot of the mess of source bridging to the drain, et cetera. So you can very easily go through the whole circuit. And so if you look at the single transistor as an amplifier, you'll essentially have a few expressions that we've sort of already derived. You just have to kind of go back and look at them. But for example, if we look at the at this transfer from gate to drain, our voltage would be what we just actually did, which is for the source degenerated common source amplifier, right? So we'll have GM or minus GMRD over 1 plus GMRS. Of course, if RS is 0, meaning that this is truly a common source grounded, non-degenerated amplifier, then my gain is just minus GMRD. Right? If I go this way, then my gain will be GMRS over 1 plus GMRS. And that's why we say source follower or common drain, because pretty much I'm getting sort of a unity gain, maybe a little bit less than that. Right? And then we said that going from source to drain, I'm going to get to the first order just GMRD. Obviously, if I was going from a real source over here that had some finite impedance, what would happen is that I would have to include that first voltage divider between RS and any input resistance into the FET. And so then we will have this situation where you have Rin over RS plus Rin, and then times the GMRD. Right? OK, so then again, if I look at R out in this case, because we assume that R naught is infinity, R out here will be infinity. If I look from this side, my R in will be what? People remember? I hear the, speak louder, you're right. 1 over GM, that's right. And then, of course, from the gate side, this is the input will be infinity. Right? So these expressions are not that hard to remember, right? You know, it's essentially one expression that you just modulate depending on where your drain, where you're going to the drain or source, right? And it's pretty handy to remember these few formulas, because then you can breeze through the whole circuit just by knowing which direction you're going, right? And just concatenate all these gains. Now, obviously, a more complex analysis will say that, OK, well, I have actually R naught that is less than infinity. And then I also have GMB that is not 0. So then I have to deal with these. And yes, formulas get slightly more complex like we derived them, but they're also kind of intuitive as well. So again, this one will be minus GM R naught RD over, or we can actually take this R naught from here just to be consistent and get 1 plus RS over R naught plus RD over R naught plus, and then in this piece we'll have GM plus GMB RS. Okay. Now take a look at this formula. And it's kind of what we already had. Minus GMRD, that's what we had also for the simpler case. And then what we have here is we've added GMB, which is kind of degrading our gain, right? Which we know that effect should. And then we have these two that are essentially negligible as soon as R naught is very big, right? So we're getting back to this formula. Right? So it kind of makes sense. Then in this side, we have something similar. Now, let's take a look at this one. You may be wondering what's R naught doing here, but it's actually pretty easy to figure out. If I had, in this situation when I'm going down, this side is, of course, this is also kind of approximate, right? I'm assuming that there is kind of ground here. So this R naught is really kind of grounded, just like any RS that I may have here. So these two actually get lumped together, are seen in the source, right, as a parallel source resistance. So then it's really GM times whatever is in the source over 1 plus GM that's in the source, and then I just add this degradation from the body. Right? Okay, and then we have this one over here, which is, let's do the RD in the end. So 1 plus RD over, again, RS plus RD plus R naught. And again, here, if we since this factor is a lot bigger than 1, and R naught can cancel with this one, become a 1, and kill these two, you really end up with something that is just like GMRD, just modified by this GMB modifier. Right. Okay. Okay, so these are kind of the small signal. Yeah.
Just a quick question: when you have common source, why is it
Common source.
the arrow pointing up on the more complex case from gate?
From here to here?
The other one, the top one, the left.
Over here?
Yeah, that one. Why is in the numerator? Why is it not RD?
Parallel.
Don't you have some intrinsic?
You mean over here? Because, well, your R naught, when you do the derivation, you will have something like that, but it's going to kind of, when you do all the cuts and stuff, that's why it shows up over here, right? Because it's really GMRD R naught over, and there's a bunch of stuff. Yeah. So again, there is a lot of ways in which we can represent. This is the way which makes it easy for me to just say, hey, I can neglect this piece, I can neglect that piece, right? Yeah. Okay, so let's wrap this up now with cascode amplifier analysis. And this time around, I'll do it so that I don't write KVL and KCL. Right, so should be able to kind of just look at the circuit and apply these formulas that we learned for a single stage, and then do it one stage at a time. Right? So the whole idea is that once you've done a single stage, you never do these derivations in your life. Okay? And this week probably was like, yeah, I don't want to do this every week, right? And so that's exactly the point, that you'll learn how these patterns look and then just go and do it, right? So we'll have, in a cascode, we'll just do the MOSFET, and bipolar, as you know, is similar, or BiCMOS is kind of similar as well. So I'm going to say M1, I'm going to call this M2, and the input be this, and then the V out. And then here, usually, we have some bias network that will just give us a solid DC voltage, right? And so I can simplify the model. Now, AV, which is VO over VI, I can do it in two stages. So I can do what's VC over VI, and C could be this node over here, times VO over VC. Now, this is just to say that, I've assumed that this is two amplifiers, right? M1 is one amplifier, the first stage, and M2 is the second stage. What's the first stage? What topology is it? Yeah. So first stage is common source, and second? Yeah. So common source is this piece, and then common gate is this piece. Right. So now that I've identified the stages, I need to apply my rules about input-output resistances so that I can properly calculate what is the gain of this first stage. Right. So, of course, I'm going to first do the simple case. And what did we say for simple case? What is GMB? Oops. 0, and R0 is also infinity. Not 2 zeros, like infinity. Okay. So in that case, if this is my first stage, what is the total resistance on this point? What is the resistance looking down? Infinite. So this is infinity. What is the resistance looking up? 1 over GM. Oops. What is the total resistance? 1 over GM in parallel with infinity, which is 1 over GM, right? So the total is 1 over GM. So my current source, my transconductor inside, which is GM V in, looks at that total resistance, which is internal R0 plus whatever the load is, in parallel with whatever the load is, and develops GM times, so let's call it GM1, times 1 over, call this GM2. GM2, right? So this is, we can call it RC because it's at this point C, right? That's my total load. And this is, we can say this is R out 1 in parallel with R in 2. Right? That's what we had at that node. Now, because we simplified things with R0 and GMB, it's not much of anything. It's very simple. But later, when we complicate it with R0s and GMBs, this will be a little bit more involved. Okay? And then, so this is our first stage. This is our common source. And then once we've derived this, now we're assuming that we're applying an ideal voltage source at this node C. So I don't care what the input resistance is anymore. I'm driving that straight with an ideal voltage source. I'm just looking forward, right? So then I can apply just the formula for the common gate where I'm directly driving the source, right? So what is that? What is the gain from here to here? Again, let's look at this. What do I see going down? Yeah, I see infinity. What do I see going up? R. So it's the total net is R, and I have looking from the bottom, I'm have a transconductor into that R, right? So then my gain is just this, GM2R. And if you didn't worry what was in the transistor, in the previous page, we did have that the source to drain, the common gate gain was GMRD, right? So that's exactly what we're talking about. Okay. And then this and this cancel out. So I'm getting that my gain is GM1R. Or sorry, I missed the sign. The first stage is common source. Okay. So this was the simple case. And now we're going to take a look at the more complex case. Just sketch it real quick again, just so we have it for reference. So the goal here is to not write small signal models. I look at these transistors and I just write out the equations, okay? Or looking up the single stage equations, if I can't remember them, I'm just going and writing stuff out, okay? So that's the goal. Okay. So what do we have here? So we're going to do GMB different than 0 and R naught smaller than infinity. Again, we have two stages, right? We have a common source and then a common gate stage. So we're going to say, okay, well, in the common source stage, we have some expression, and that is again, the minus GM of this guy, which we know is just small GM1, so we're going to write that out, times, and then this total resistance that I'm seeing here, right? So I'm just going to call it RC for now. And I know that, so if I draw things out, this is R out 1. This is R in 2. This RC will be equal to R out 1 in parallel with R in 2. That's the total that transconductor sees as load. In this case, our R in 2 is just like our RL, and our R out 1 is just like the internal output resistance of the first stage amplifier. And then I have CG. And there I have its own transconductance times R out. So I'll write it like times R out 2. So now R out 2 is here. And of course, I have this R, so I'll have to write R out 2 in parallel with R. So these are just generic formulas, right? This is a second stage amplifier. It has its own capital GM2, and there is a parallel load R. So I'm just writing this out. Now we're going to see what this capital GM2 is and what R2 is. Right. So if I go back and take a look at what the input for is over here, in a more complex case, oh, I actually didn't write that out. So let me just write it out. It was R0 plus RD over 1 plus GM plus GMB times R0. So we can use this. This is the input. And obviously, if GMB is 0 and R0 is infinity, these two cancel out. RD doesn't matter. So I'm just getting 1 over GM. Right? That's the simplification here. So I'm going to use this one over here for R in 2. So I'll write it over here. So it's R02 plus R, which is this RD. And then R out 1 will be just R01. So I'm going to have R01 in parallel with R02 plus R over 1 plus B2 times R02. Now, I don't really need to write all this because I should know from the get-go that this R01 is much, much bigger than something that's approximately 1 over GM, right? Or 1 over GM plus GMB, right? So I could just safely say I don't care about this R01, even in these more complex expressions, okay? And then if we look at this overall gain over here, again, I can go back and take a look at this expression. So I'm going from here up. And this is the expression for the common gate amplifier. So I'll have 1 plus GM plus GMB R naught times R over, and we're going to do these are 2's. This R02 plus R. Now, notice that because I've neglected this piece, this is actually pretty nice. These two will cancel out. In this one, this part is exactly the same as this one. So I'm really just left with minus GM1 times R. Now, this just tells you that even with these really fancy additional elements, my gain is really just minus GM1R. But that gain is not really the most important piece about the Cascode. The most important piece is what's the output impedance. And we hinted that a little bit yesterday at kind of the office hours. But again, the output impedance is R01 plus GM 2 plus something like this, okay? And then we'll say, okay, well, this is approximately the same as just GM2 plus GMB2 R02 times R01. Now, you see, this factor over here kind of multiplies up the output impedance of the first stage. Or you could say that the output impedance of the last stage, second stage, gets multiplied by this other factor. It doesn't really matter. But the point is that the intrinsic transistors R0 effectively gets amplified by another roughly GM R0. Okay, and GM R0 is the intrinsic gain of the transistor. If nothing was loaded to the transistor, that's kind of the gain that that transistor would create, right? Because it's current GMV1 would flow just through R naught. So that gain is actually the highest you can get. Anything you attach to that output will just lower the total output resistance. It will decrease the gain, right? So this is a pretty powerful way to increase the output resistance. And you'll see in the next few lectures when we do the current sources, this is used all over the place to boost the output impedance, because as you know, current sources have infinite output impedance, right? Okay. I think we're out of time, so next time around I'll cover the FTs of the transistors, and then we'll go quickly, and then we'll go into other topologies like differential amplifiers and things like that, and do some bisection analysis, things like that.